This is a video about the path product and what I will call homotopy equivalence. Sometimes homotopy equivalence refers to maps between topological spaces as well. Here I'm going to focus on the equivalence relation that is induced by two curves being homotopic. Let's make sure though that everybody watching this video understands what those words mean. So let's let X be our topological space. Its topology here is T, but like in the previous videos, we won't do too much with that topology T. Let's let A, B, and C be points in our topological space. Let's let gamma naught be a path from A to B. Remember, that's a continuous function that starts at A and ends at B, and it takes inputs from the real numbers between 0 and 1. Let's let gamma 1 be a path from B to C. Then recall the path product, we'll denote it by gamma naught, gamma 1, just concatenates these paths, gamma naught and gamma 1, as gamma naught, gamma 1 of t. I just need to go at double speed around gamma naught, so gamma naught of 2t if t is between 0 and a half, and gamma 1 of 2t minus 1 if t is between 1/2 and 1. And you can see in my visual to the side that we're just going around gamma naught and gamma 1 both at double speed so that it takes 1 unit of time, if you want to think of the input as time. It just takes 1 unit of time to traverse the concatenation of the two paths. Now, warning, the path product is not associative, and that's really what the remainder of this video is about. So what does that mean? That means that it's possible to find paths, gamma naught, gamma 1, and gamma 2, for which the path product makes sense, but it matters what order you put the parentheses in. It matters where you plop the parentheses. Now, plenty of cool things are not associative. For example, rock, paper, scissors. But if we're going to try to study a binary operation, which, I've got this path product, it's a way to put paths together, kind of looks like a binary operation, the corresponding algebraic structure with the richest theory to offer us is a group. But groups require that the binary operation be associative. Now, in case you'd like to see how associativity fails, it's not too hard to come up with an example to show this. So let's say gamma naught is just a path from A to B. It doesn't really matter my topological space. You could argue that it does, but maybe take my donut example from the picture and before. Let's say gamma 1 is a path from B to A, so just from B back to A. And let's say gamma 2 is just the constant path that just stays at A the whole time. Now let's look at what if I do the path product of gamma naught and gamma 1 first. Remember, that just says, okay, go around that at double speed, and then go around gamma 2 at double speed. And what that says is that, well, you stay at A for the last half of the journey. And here, if you look at the visual, you can see that once the input gets to a half, you're already at A, and you just stay there for the rest of the time. Now let's look at what if I put the parentheses around gamma 1, gamma 2. Now, how you read that, that means that, well, you go double speed around gamma naught, and then you go double speed around the path product, gamma 1, gamma 2. And if you think about what that gamma 1, gamma 2 path product looks like, well, if you're going to go around that at double speed, that means you have to go around each gamma 1 and gamma 2 at quadruple speed. And so at the very end, just what I want to notice, there are other things you could notice to see that it's different from the orange that we talked about earlier, but the very end says that you stay at A only for the last quarter of the journey. And so here is a visual of how this path product works, where again, once I get past 3/4 is when I get to A and I stay at A. And again, that's different than the path we had above that was in orange. So what's going on here? Like, why? How did this happen? Well, the counterexample is trying to illustrate that the choices of parameterization is the obstacle preventing the path product from being associative. So if we think associativity is good because, like I said, a group has kind of the most tools for us to offer to start doing some math and analyzing things, we need to think of a way that's going to ensure the path product doesn't care about parameterizations. In other words, the route from A to B to C is all that matters, not the way that you choose to traverse that route. So that sounds like we're going to do some kind of an equivalence relation. So how might we define what it means for two paths to be equivalent? Well, in a previous video, we introduced what it means for two curves to be homotopic to each other, and we're going to recall that definition here. So same setup, and I've got two paths, gamma naught, gamma 1, and they both go from A to B. A homotopy from gamma naught to gamma 1 is a continuous map, F, it takes two inputs, two real numbers between 0 and 1. The first input we'll call S and the second input we'll call T. And it spits out a point in your topological space. And it's going to satisfy four conditions. The first one is that it starts at A. So f of 0t is equal to A for all values of t. Secondly, it ends at B. So f of 1t is equal to B for all t between 0 and 1. Third, f of S0 should be the starting curve, gamma naught. And f of S1 should be the ending curve, gamma 1. Now f's assumed to be continuous in this definition, so for fixed t, we have that f of st is a path from A to B. And so thus we can refer to each point f of st as gamma t of s. So in other words, f of st equals gamma t of s. And that is the point on the curve, or I'm sorry, that's the point in x that is on the path gamma t, say at time s if you want to think of it that way. To get another idea about what a homotopy between two curves gamma naught and gamma 1 is, on the left side I'm saying if you take a specific t and let s vary between 0 and 1, that is a path from A to B. And now what I want to visualize is I get a different yellow path for each value of t. And what you see is as you let t increase from 0 to 1, you see that those paths start at gamma naught and they continuously deform until you get down to gamma 1. On the right side, we're going to go kind of the other perspective. Given a specific value s between 0 and 1, s determines a point on each of the paths gamma t, so on each of the paths in that family. So now as you let the s's vary from 0 to 1, you see that all the points on the paths in the homotopy, all the points start at A and wind up going towards B. All right, so let's look at our first theorem here. The relation that gamma naught is homotopic to gamma 1. Here this squiggly means homotopic. Kind of looks like an isomorphism, but with one less squiggle. We're going to show that this is an equivalence relation on the set of paths in X. And so that means, 1, it should be reflexive. So gamma should be homotopic to itself for any path in X. Number 2, it should be symmetric. So for any paths gamma naught and gamma 1, such that gamma naught is homotopic to gamma 1, then gamma 1 should be homotopic to gamma naught. And number 3, this homotopy should be transitive. And so for any paths gamma naught, gamma 1, gamma 2, such that gamma naught is homotopic to gamma 1, and gamma 1 is homotopic to gamma 2, then gamma naught should be homotopic to gamma 2. And we'll go through the proof of this. So number 1, take a path gamma that goes from A to B. And let's just let the homotopy f just always be gamma, just that curve. So it's like a constant homotopy. And so I'm saying let every curve in the family that is the homotopy just be gamma. And so why is this a homotopy? Well, we have to make sure that it satisfies the four conditions from the definition. So when you plug in 0 for s, well, you just get A, because you're always at gamma 0. And you know that gamma starts at A. So f of 0t is A for all t. When you plug in 1, same reason, you just get B, because gamma ends at B, and all the paths in your homotopy are gamma, or it is gamma is maybe the better English to say. Number 3, when you plug in 0 for t, well, you're on the curve gamma, the starting curve. Again, all the curves in the homotopy are gamma. So finally, number 4, when you plug in 1 for t, you end at the curve gamma. Well, that's not surprising, since again, all of the curves in this homotopy are just gamma. So thus, this constant f is a homotopy from gamma to itself, meaning gamma is homotopic to itself. Let's look at a slightly more interesting one. How do we show that homotopy is symmetric? So let's suppose that gamma naught is homotopic to gamma 1. Well, that means that you can get your hands on a homotopy f from gamma naught to gamma 1. And why don't I just take 1 minus t as the input? That is going to be a homotopy that starts at gamma 1 and runs back to gamma naught. So gamma 1 is homotopic to gamma naught. Finally, number 3, suppose that gamma naught and gamma 1 are homotopic, and gamma 1 and gamma 2 are homotopic. That means that, again, you can get your hands on a homotopy f from gamma naught to gamma 1 and a homotopy g from gamma 1 to gamma 2. And what we're going to do is we're essentially just going to take the path product of those two homotopies. So we're going to do the homotopy F at double speed, and we're going to then follow that with doing the homotopy G at double speed. And just over to the side, if F corresponds to a family of curves gamma t that go from, alpha t, goodness, my Greek letters, alpha t that start at gamma naught and end at gamma 1, and if G represents the family of curves beta t that start at gamma 1 and end at gamma 2, then what is this H doing? This H is just the family that represents the path product of each alpha t with each beta t. So that's how you should think about what H is, in case the other way I said it doesn't make sense. Okay, so notice H is continuous because its pieces are, and these pieces agree at t equals a half, since when you plug in a half, the F formula reduces to F of S1, and F is a homotopy that ends at gamma 1 of S. But then that's the same spot where G begins, and that, when you plug in t equals a half, that's G of S0. So these two things match. That's good. So continuity is not a problem. So the last thing we need to check is that H satisfies the four conditions in the definition of a homotopy. And just observe, when you plug 0 in for S, that reduces down to A in both piecewise formulas, or in both pieces of the piecewise formula. When you plug in 1 for S, that reduces down to B. When you plug in 0 for t, you get f of s, comma, 2 times 0, but you know that f is the homotopy that begins at gamma naught, and that's what we want. So my homotopy H also begins at gamma naught. And when I plug in 1 for t, kind of like the final value for t, well, that's what happens when you plug in t equals 1 into your piecewise formula where G is, and that reduces down to gamma 2 of S, because I know that G ends at gamma 2. G is a homotopy that I know ends at gamma 2. So that means H ends at gamma 2 also. And so that finishes the proof. That shows that H is our homotopy from gamma naught to gamma 2. Finishes the transitive proof. Now let's refer to this equivalence relation as homotopy equivalent. Now denote the homotopy equivalence class of a path gamma just by putting brackets around it. That's typically what you did in like a proofs class when you learned about equivalence classes. So what we're going to show now is that homotopy equivalence, as we've defined, these equivalence classes, they don't care about different parameterizations of a path. And so a proposition here, to make that a little bit more formal, if you've got a path gamma, then it's homotopy equivalent to any reparameterization of itself. And the way that we're going to prove that is, well, any reparameterization of gamma has the form gamma of p of s, where this function p is a function that takes a real number between 0 and 1, and it outputs such a number as well. It's continuous, p of 0 is 0, and p of 1 is 1. Now, to show that gamma is homotopic to this composition, gamma composed with p, in other words, that's the same thing as saying that gamma and gamma composed with p are in the same equivalence class, so their brackets equal each other. We got to define a homotopy f that goes between them. Well, why don't we just take f of st to be gamma of the quantity 1 minus t times s plus t times p of s. Observe f is continuous since gamma is continuous, and the input is some linear thing that's continuous. So it's a composition of continuous functions. And let's go ahead and satisfy our four conditions for what it means to be a homotopy according to the definition. Well, f of 0t, is it A? Well, when you plug in 0 for s into our formula above, I know that p of 0 is 0 by definition of p. So this just reduces down to gamma of 0, and gamma is a path that starts at A. So that's why that equals A. Number 2, we've got to verify that when you plug in 1 for s that you get B. Well, same thing. Plug in 1 for s into your formula, and what you know is that p of 1 is 1 by definition of p. So this stuff just reduces down to gamma of 1, and you know gamma ends at b, so we're good. Number 3, got to verify that when you plug in 0 for t, do you start at the curve gamma? And when you plug in 0 for t, you see that the p of s term gets knocked out, and so you're just left with gamma of s. Finally, when you plug in 1 for t, do you end at gamma composed with p? And when you plug in 1 for t, notice that the term that just have s gets knocked out, and you're only left with the p of s term inside the parentheses. So this homotopy ends at the composition gamma composed with p. And that finishes that these two curves are homotopic to each other. In other words, gamma is homotopic to any reparameterization of itself. So next, what we're going to do is we're going to extend the path product to homotopy equivalence classes. And so if you've got gamma naught, gamma 1, and that path product makes sense, then why don't we just say the path product of two equivalence classes, gamma naught times the equivalence class of gamma 1, let's just say that's the equivalence class of the path product gamma naught, gamma 1. So that should be really similar to how you probably defined like addition or multiplication mod n for integers, right? Why don't I just do the operation I know and love on the equivalence classes? And you just got to think about, is it well defined? And in this case it is. Finally, we'll show that this path product on these equivalence classes is associative. Again, whenever the path product makes sense. So just to recap, path product on its own, without talking about equivalence classes and homotopies, path product, not so good, not associative. However, when you think about doing the operation on the homotopy equivalence classes, then the path product's fine. And that's what we're going to prove, that it is associative. And so let's say you've got your three paths, gamma naught ends where gamma 1 begins, and gamma 1 ends where gamma 2 begins. Then, when you take the path product of the equivalence classes of those three curves, then it does not matter where you try to stick in those parentheses. In other words, this operation is associative. So let's look at the proof of this. Now, the above equation, so I'll try to make sure it's on the same screen here, is equivalent to, I can move around the brackets according to how we defined what the path product is for equivalence classes. I can move those brackets around if I need to, and this is going to be a little bit more convenient for us to show. Now, rather than finding a homotopy between these two curves, what we're going to do is think about what we've already done. And what we know is that it suffices to show that gamma naught, gamma 1, gamma 2, with the parentheses there in purple, it's probably what I should have just said, that is just a reparameterization of the orange curve. And that's supposed to kind of follow the logic what we did in our example. It said, it kind of illustrated that, look, the parameterization is the thing that the associative is getting mad about. So what we're going to do is we're just going to show these two things are reparameterizations of each other. But again, namely that the purple is a reparameterization of the orange. So what we're going to do is we're going to find a function p that allows me to make that reparameterization more concrete, right? What do I compose with so that the purple is the orange composed with p? Now let's compare the formulas for each side of this equation. And so if we kind of pull along on the orange formula here, and remember, you got to go around gamma naught, gamma 1 at double speed, then at gamma 2 at double speed. But that path product, that means you have to go around gamma naught and gamma 1 at quadruple speed, and then gamma naught at double speed. So that formula works out to this. Now if I look at the purple, that says you're going to go around gamma naught at double speed, but then you've got to go around the path product gamma 1, gamma 2 at double speed, which means that you've got to go around gamma 1 and gamma 2 each at quadruple speed. So that formula looks like this. Now what we're going to do is we're just going to compare. I want these formulas to look the same. And so I want each of these colors to line up here. And so if I demand that 4 times p of s, the first input from the orange function, is equal to 2 times s, the first input from the purple function, let's see what we get. So we can solve that for p. So let's get our expression for p, and let's think about when does this hold? If I scroll up a little bit, well, that's supposed to work whenever p of s is between 0 and a fourth. But if I plug in this new formula for p of s, that's s of 2, and if I rearrange stuff, that's equivalent to s being between 0 and a half, and that matches the criteria for the purple function that we had for gamma naught. So that's good news. So we've got our first piece of what p should look like. P should look like s over 2 whenever s is between 0 and a half. Now let's look at the blue pieces. So if you look at the blue pieces for a moment, what you should come away with is 4 times p of s minus 1 has to be the same thing as 4s minus 2. Solve that for p of s. And we've got our next piece of the function p is s minus a fourth. And if we think about that has to be true whenever p of s is between a fourth and a half. If you plug in that new formula for p of s and rearrange it to get s by itself, you see that it matches the condition that the purple function had for s. that works for the s's between 1/2 and 3/4. Finally, from the yellow, we're going to solve 2p of s minus 1 equals 4s minus 3. Solve that for p of s and you get 2s minus 1. And we think about when this holds true. Well, the orange function wanted p of s to be between 1/2 and 1. If you plug in your new formula for p of s and rearrange, you get that that is equivalent to s between 3/4 and 1, which is exactly what the purple function wanted from us. So in all, let's take p to be this function, putting the pieces together and the domain for each piece. Now what we're going to do is we're going to finish the proof of this theorem by using the previous proposition. When we look at the class of this orange path product, that's the same thing as the class of any reparameterization of that orange path product. And that's the previous proposition at work. But what we also just showed is that that reparameterization is exactly the purple path product. And that's what we wanted to show to conclude associativity.